Okay, we just finished with page 2, and now we're going to talk about chemical equilibria. In particular, looking at the liquid-gas equilibrium for a liquid in a closed container. So in picture A, we have the water molecules shown, and there's some air over the surface of the water. The water will evaporate into that air until it reaches a certain vapor pressure. And how much water is in the air, is in the vapor phase, depends on temperature, but it's a fixed amount. At a given temperature, it's tabulated and we know how much water will be in the vapor over that surface. So initially the water molecules evaporate or vaporize into the vapor, and then as there become a lot of water vapor above the surface, then they begin to condense back. And that process is dynamic equilibrium. It's dynamic because the molecules are still condensing and vaporizing individually, but overall the total amount is constant. So that's what it means to be at equilibrium. The amounts are no longer changing. At the equilibrium point, everything is present at once. There's liquid and vapor present in the system. Now, if it was an open system, the water would just evaporate away because that much water could not establish the required vapor pressure in, say, a whole room. So that dynamic exists in the closed system. So here we get to our definition of equilibrium. Well, there's a couple. The concentrations of the reactants and products are no longer changing in time. And that means that the rate in the forward direction equals the rate in the reverse direction. So here's an example. We are looking at this equation of SO2Cl2 in equilibrium with its decomposition products, SO2 and chlorine gas. So we have our initial concentration, our initial conditions, and that has 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules of SO2Cl2. After 5 minutes, we have 1, 2, 3, 4, 5 SO2Cl2. Let me get to it. And we have 1, 2, 3 SO2 molecules and 3 Cl2. After 5 minutes, that's not at equilibrium. Here's the equilibrium. So let me erase that. But here's the equilibrium mixture. Yeah, so I'll count that one. And in that one, it looks like we just have 2 SO2Cl2 molecules left, right? There and there. And then we have 1, 2, 3, 4, 5, 6, 7 SO2s and 7 Cl2 at equilibrium. All right, so 15 minutes later, it's going to be the same. Now, what if we started with 9 SO2 and 9 Cl2? So in this case, we're starting with all reactants and all products and 0 reactants there. So it's still going to reach an equilibrium. It's just going to react backwards to do that. So at the end, that one will also have just 2, 7, and 7. All right, and then we start with our reactants, and again 2, 7, and 7. So this is really just making the point that that amount at equilibrium will not change. And they're all there in the container together at the same time. Okay, so here it is graphically. And we are asked to indicate on the plot below when is equilibrium achieved. So we're looking for that concentration to stop changing. So who knows, maybe about there. As soon as that concentration line is flat. Okay, so let's introduce the equilibrium constant. For the general reaction shown, there's the law of mass action, which is describing the products over the reactants using those coefficients from the equation to indicate the powers of dependence on those concentrations. And the concentrations here, the square brackets, indicate molarity. So let's go ahead and write the K expression. This is Kc because it's in terms of the concentration. Sometimes we'll see these also described as Keq. It could be a Kc for concentration, Kp for pressure, or we have like a Ksp as the solubility product for a solid. So lots of different designations for those K values. And they all take this form, basically the products over the reactants with those coefficients showing up. So for this one, we'll put the products on top, and those are multiplied over the reactant. Now this next one has coefficients, so we have to be sure to include those. So this will have the ammonia on the top squared over the reactants, and that hydrogen gets cubed. So that is the equilibrium expression. So some of the characteristics of the Keq or Kc is that will be constant at a given temperature. These problems will include a temperature, and you may not need to use it in the calculation, but it will always be given because the equilibrium constant is only valid at that temperature. Otherwise, the value changes. Let's see, the size of the equilibrium constant indicates the extent of reaction, so how much goes to products. So if we're going to think of something as large, a large Kc value, we can think of 10 to the third or greater. Sometimes we even go all the way to 10 to the fifth. So if it's a large K, then that means it goes to products, right? Because products are on the top. A large value means there's lots of products compared to the reactants. For a very large K, reactions go essentially to completion, a one-way reaction. For a very small K, 10 to the minus 3 or 10 to the minus 5th or smaller, the reaction mixture has more reactants, so it basically doesn't go very far. So just a tiny amount of products. But for an intermediate value, then everything will be present in the container at the same time. So the reaction occurs, but as soon as products are formed, they start to react back to reactants. So here's some pictures to show. Oh, and let's say that if it goes to products, we're going to say it lies to the right. And if the K is small and it does not go very far towards products, then it lies to the left. Now this is the reaction we were looking at before, and its equilibrium values were 2, 7, and 7. So does that lie to the right or the left? They're pretty equal, right? They're not 1,000 times different, but they lie slightly to the right, slightly towards products, but it's fairly balanced. All right, what about the eggshells? Calcium carbonate, that was our eggshells example. And we said That basically doesn't decompose on its own.
So that one lies to the left.
That's right. So it stays mostly reactants.
So when it lies to the right, it's just saying that it's staying, like it doesn't reverse back into reactants at the same speed that it stays as a product.
Well, when it reaches equilibrium, you said the word speed. When it reaches equilibrium, the rate forward and the rate reverse are the same,
Right. Okay.
but the concentrations might end up looking like this: a big arrow one way and a small arrow back is one way to think of it. Or if it's a very large K, then maybe you would just have a one-way arrow. In this case of the eggshells, this basically would have a back arrow. It's the forward arrow is so tiny, it's basically not going to react. So that's another way to think about, does it lie to the right or the left? Is it a one-way arrow, or are they both equally? Is everything present?
So for our penny thing, that's the basic time frame that we're talking about in equilibrium. That they're moving back and forth at a certain
Yeah. Yeah, with the
unchanging
simulation.
rate. There we go, unchanging in time.
Yeah, and we had to slow it way down, so we took each time step and we had to prepare. But of course, some reactions go very quickly. That one ended up with also, when we have these numbers like 2 and 7, and that was something like 14 and 9, they're relatively, I don't know if you can hear the puppy yowling over there. Yeah, so they're pretty balanced. When we talk about chemical reactions, though, we're thinking about like Avogadro's number worth of particles. So for something like a weak acid, there are 10,000 reactant molecules for every one that splits apart into ions, and yet we still have a lot of reactions going on. So if it were literally ratios of like 14 to 9 or 2 and 7, it would be pretty balanced. It would be an intermediate K value. So we'll get deeper into those. But for now, let's write the equilibrium expression for these reactions and then compare them.
Equilibrium expression is just like the Kc or K equal. Oh, you're doing it right now. Sorry.
Oh yeah, no, that's right. Right, so how do these compare to one another?
They're inversed.
Yeah, they're inverse.
Opposite.
So KEQ equals 1 over K prime EQ. So when we flip the reaction, when we reverse the reaction, we invert the K. And that makes sense because if you think of it as products over reactants, you've reversed those. So then you would write your KQ for the equation as it's written. So those are reciprocals of one another. Now some of those had pressures, and I used molarity, which is fine. You can talk about the molarity for a gas, but we can also represent moles for a gas in terms of the partial pressures. So if you have all gas phases, you might want to be working with Kp, the partial pressures of those gases. And so let's write the same kind of expression, but now these are all just gases, so we'll write them as pressures. So this one will have pressure of water squared over pressure of hydrogen squared times the pressure of oxygen. All right, the next one's got a few more terms. So those exponents can reflect really big changes with a change in concentration or pressure. That oxygen to the 5th power is going to change very quickly. So in order to go between Kc, equilibrium constant with concentration, and Kp with pressure, we will use the ideal gas law to convert between our molarity and our pressure. So wherever there's a pressure, we can, well, here's our N over V, there's our molarity. But we get this factor of RT. So here I'll write the molarity of C to the L, and then I'm going to have a factor of RT. And I'll do the same thing for D. I'm going to make that into the molarity, moles over liters, of D, and a factor of RT to the M. And our reactants to their exponents with the RT factors. So if we group those and we bring that Kc together, then let's see, maybe I should write that out in line. Oh, I forgot my D to the M. To the J. Then I have RT to the L plus M and RT to the J plus K. So there's my Kc value right there. And there's going to be a factor of RT, and I'm going to group those exponents again. It's going to be L plus M minus J minus K, where J, K, L, and M are the coefficients in the balanced equation. So we can also think of this factor as the difference in the number of moles of gas. And these have to be just for gases. If you had a solid in there or an aqueous component, then that would not have a factor of RT with it. It would only apply for the gases. So we're looking at this difference in moles of gas, where our delta N, difference in moles of gas, is the sum of the products minus the sum of the reactants. So let's take a look at it for these equations. Our delta N for A is just 2 minus 1 equals 1. For B, we have 2 minus 4, so that is minus 2. So we'd have 1 over RT squared. Delta N for C is going to be 2 minus 3 is minus 1. And in the last one, we have 7 minus 6 is plus 1. All right, and I think that's all. This is where the next video picked up, was on page 8.
That's correct.
Yeah, so we're all set.
What does the change in N there tell us at the end?
That tells us how many factors of RT it takes to convert from our Kc into our Kp. So basically we're wondering, did we gain moles of gas or did we lose moles of gas? Because in the equilibrium expression, if we're working in pressures, we'll have that factor of RT. So this is our Kc. Maybe we're given a Kc and you need to calculate what the Kp would be. You need to know what the change in moles of gas. So all those factors of RT will cancel out except however many the change represents. Does that make sense? We have a formula, and I'll give you the formula, but I always just derive it each time because I just can't remember how to plug in the formulas correctly. It's so silly. But it seems pretty straightforward when I remember that I have this N over V as my molarity. Then I just stick an RT factor on each one of them, like concentration of C times RT to the L. That is that pressure. So I really just substituted in the ideal gas law.